Having said that, statistics cannot be away from misleading statistics, because it very much depends on how data is actually being collated, data is being wrangled, data is being interpreted, and how this, most importantly, how this data is being classified. We shall be looking at two misleading statistics. The first one involving issues with discrepancy between using two variable analysis versus a three variable analysis. The next case involve the inherent nature of correlation in arriving at a conclusion. Let's look at case number one. Suppose you're involved in a drug trial evaluating the effects of two antihypertensive drugs, X and Y, and you're supposed to decide whether these two drugs are effective or otherwise. So since this one is comprised of three groups and you are only considering the drug factor, so this is an obvious candidate for one-way ANOVA. So you key in data this way, and then after that, subject them to analysis. And once you have conducted the analysis under SPSS, you notice that in terms of statistical significance, this analysis is not statistically significant because the significance value or the p-value here is more than 0.05. In order for the values to be, the statistical changes to be meaningful, it should be less than 0.05. In this case, this is obviously more than 0.05. So that means you do not reach the minimum 95% confidence level to conclusively say that the three groups are different from each other. So in this case, you decided to bend the rules a little bit and analyze them as separate pairs. So you use t-test to compare X and control, and then followed by Y and control. And what did you find? Something interesting came up. You notice that when you compare control and X, the significance is actually barely significant. In fact, it goes below 0.05. Remember, our alpha in this case is 0.05, meaning that you have a 95% confidence level saying that your test results are statistically significant. So in this case, obviously, it's significant. And likewise for Y as well, when it's being compared against control. However, when you extend it between X and Y, there are no significant difference. So why is it so? Remember, when you analyze X, Y, and control together, there are no statistical significance. But when you compare X and control or Y and control using t-test, you notice that there are statistical significance. However, when you compare X and Y, there are no statistical significance. So what does this tell you? Which results should you use and what should you do? In order to understand all this, you have to go back to the underlying or fundamental assumptions of doing statistical testing. And this is actually where data analysis and experimental design is actually something important. Experimental design should be decided at the onset when you are defining your study. Okay, in this case, you are trying to compare X, Y, and a control. You need three groups. And for all you know, X, it could be the old drug, Y could be the new drug, and you want to compare the two. Okay, you want to compare the two. Or maybe X could be a titrated lower dose version of Y and so on and so forth. And there are so many possibilities. The first thing is you need to define what will be your aim. Even though some may argue that you are actually, when you are comparing one-way ANOVA, doing one-way ANOVA comparison, you are comparing all three groups at the same time. And when you are doing multiple t-tests in what we are doing here, we are actually making a legitimate three-group comparison in its three steps. You have to remember the inherent characteristics of how the significance and degrees of freedoms are being derived. In this case, it is obvious that the t-test becomes significant because you are not testing at 95% confidence level. When you are doing a one-way ANOVA, you are testing at 95% confidence level. But when you are doing a one t-test, is 95% confidence level. Two t-tests, it is actually 95% confidence level multiplied by another 95% confidence level. If you do 3 times of t-test in order to make sure that you can compare X, Y, and control, then your actual confidence level will be 95% confidence level for test for the test of comparison of first pair, multiply by 95% confidence level for the comparison of second pair, and a 95% confidence level for the comparison between the third pair. So in short, you may end up with only a confidence level of 0.85, about 0.85, 0.87. So in short, you are no longer testing at 95% confidence level when you split the three parameters into three pairs and analyze them separately as three pairs. You are testing at 85.7% confidence level. So obviously, if you're checking at lower confidence level, the data will become easily significant. So it becomes important for us to go back and look at the objectives again and see what will be the most appropriate data array and experiment design in this case. Now, let's move on to case number 2. This is actually an obvious case involving correlation, and it is actually common across the board. What happened here? Well, you design a study to investigate a probable relationship between exposure to cigarette smokes in pregnant mothers. It is known that high blood cotinine, which is actually a nicotine metabolite, will increase placenta weight and surface area. You try to correlate adjusted placenta weight versus blood nicotine metabolite levels. It is known that by having higher blood nicotine metabolite levels, then you are going to have higher adjusted placenta weight. The term adjusted placenta weight is used because you also know that babies, the placenta, and the mothers will be having various sizes. So it becomes important for us to use weighted or adjusted placenta weight. So you key in the data in the following manner, since this is actually correlation, and run the correlation as indicated on the screen. So, and then after that, you go for a simple plot. What you found out during your inferential statistics investigation is that exploration is that you have an outlier based on this box plot. Remember, box plot, the lower and upper limit of box plots indicates where 95% of the distribution, 95% of the populations are. So if let's say you have this one particular dot outside the 95% limit, that means that this could be a potential outlier. And who are the potential outliers? If you look at this particular slide, it is actually value pair number 7. Okay, cotinine 53, and then the placenta is 1.7. Okay, so it is actually this value that contributed to this particular outlier, and it lies outside 95% of all other values based on these box plots. And then when you do your scatter plot, again, you note that it is actually an outlier. Remember, when you are constructing a correlation, you are trying to draw a line through as many dots as possible. So if you have a stray dot either above the line or below the line, it will greatly skew the placement of the lines. This is actually the inherent weakness of correlation, and therefore may affect your derivation or your interpretation of results. Now, let's see what the computer tells us about the correlation. Remember, at the assumption, we are assuming that by having higher cotinine, it will actually correlate positively with the placenta weight, because higher cotinine inhibit oxygen transport, and therefore placenta has to become thicker in order to accommodate more blood flow to transport more oxygen to the babies. So in this case, what you can find out is that in your first analysis, there are no relationship between placenta weight and nicotine metabolite levels as indicated here, because the significance values, the probability value here is 0.511. In order for the correlation to become significant, this sig-2-tailed value is supposed to be below 0.05 or 95% confidence level. So what do? You decided to remove the outlier. Remember that pair number 7 has an outlier. So you remove that outlier. Okay, and now you look at what happens to the correlation results. Not only that, the correlations becomes much more powerful with a correlation coefficient of 0.751. The values are also statistically significant, which is actually indicated by this circle here. So you have to ask yourself, is this justifiable to delete your data? And is this cheating? This is again something that you have to ask yourself, and this is actually where statistics may not be able to help you. Remember, when we remove the outlier, we are actually investigating what is actually going on. This is actually where you need to use the statistics or the data as something that is living instead of treating them as numbers. Now, this cotinine is actually a secondary metabolite of nicotine, which is actually a toxic substance coming from cigarettes. And from literature search, we know that any values of cotinine above 50 is already neurotoxic, okay, or toxic to the nervous system of the mother. And obviously, this number of 53 with a very, very small placenta weight is something that deserves to be investigated. It may not be a true value. So based on that, we deleted this value and we adhered or published these results as correlated, the significant correlation between placenta weight and nicotine. So what message I'm trying to portray here is that you need to look at your data from scientific basis. You need to have the ability to explain your data and justify your data, and of course your analysis as well. And sometimes you need that skill to explain your results, and that is actually what going to differentiate you from other scientists or other people who are doing or conducting similar research. So I hope with these two explanation of misleading statistics, you have gained some degree of insight into the importance of having well-defined prior data array and experiment design. And number two, you need to have in-depth understanding of how your data came about so that you can justify, to include, to exclude, or to operate your data as how you see fit and making it make sense in real life. So that will be the concluding remarks that I want to share with everybody. So in this case, I already mentioned earlier, applied statistics is not only about significance testing. It's about analyzing and then using the results to logically explain real life situations. Remember, whatever that you do, you should be able to see this in real life. A test can be mathematically and statistically sound, but if it can't explain real life situations or give a distorted picture of a real situation, it is useless. And it is important for us not to hold overzealously to true statistical principles. Remember, statistical significance does not mean practical significance. We are doing research, and research only makes sense if it solves problems or if it manifests in the real world.